Here's another example. A 2 kilogram ball is thrown down at 3 meters per second from 60 centimeters above an uncompressed spring. The ball strikes the spring and compresses the spring a distance of 10 centimeters before shooting back up. Determine the spring constant of the spring. Alright, so here's the picture. You've got a ball here, and the ball is being thrown down at 3 meters per second. This is a spring, it's vertical, and it's uncompressed. Then the ball speeds up as it goes down, it hits the spring, and because it's moving, it compresses that spring. But the ball can only compress the spring so far. Once the ball reaches this point, 10 centimeters of compression, the ball has stopped, and it's about to go flying back up in the air. And we have to figure out what is the spring constant of the spring. Now, we start out with more than just one energy, and let's take a look. Our first step is to label the initial and final positions. Here's our initial position in the picture, and this over here is our final position where the ball is at the end. At the beginning, what energies, what things does the ball have? And remember, we're looking not just at the ball, but also the spring, because that's part of our system. What do we look for? Speed, height, compression. Do we have speed initially? Yes, we do. So I put down V initial. Do we have height initially? Yes, we do. We have height as well. Right? The ball is at some height. But we have to determine what's our zero level. And just like before, we'll take the bottommost position that the ball reaches as the zero level. So initially, how high up is the ball? Well, we have to consider from that red line I just drew, where is the ball to start? How high up vertically? We start at the line, we go straight up till we get to the ball, and that is our initial height, H initial. So we have both initial speed and initial height. What about compression? We don't have any of that initially because the spring starts out uncompressed. Okay, at the end, our final moment. The ball has stopped, so we do not have any speed, so I do not write down speed, VF. Do we have any height? From this red line, we are 0 meters up. We're some initial height up over here, but at the final moment, we're 0 meters up, so there's no height. Compression, yes, we do have that. The spring is compressed. How far? Has it compressed 60 centimeters, 10 centimeters, the sum, the difference? Well, the spring started out right here, where my cursor is, and it went down to here. So the compression is just 10 centimeters. So we do have compression. Let me write down X final. Okay, now I turn to my equation. We said there's initial speed, so I want to include that term. There's initial height, so I include that term. This is all 0 because there's no compression at the beginning. There's no final speed, so this is 0. The final height is also 0, and we do want to include this because there's final compression. So I write that equation with just those three things. 1/2 k x final squared. Now you might be wondering, can we cancel out the 1/2? But if you try to do that, if you try to multiply both sides by 2, it will go away here, but you have to distribute the 2 to every term. So you'd have an extra 2 right here. So that's not super useful to us, so let's not try to cancel out the 2. Instead, we start to figure out what do we have, what do we need to know. We know the mass, so we know that. We know the initial speed, it's 3. The initial height, is it 60? Is it 10? Is it some combination? Well, you start at the bottom and you measure the initial height all the way up to the ball. So it's 60 plus 10. But you can't put that into centimeters. When you plug into the equation, you have to plug the initial height in as meters. Centi is equal to 10 to the negative 2. So it's replaceable with 10 to the negative 2. Instead of multiplying by centi, I'm going to multiply by 10 to the negative 2. So I just substituted in for centi. And I move the decimal place to the left to 0.70 meters is my initial height. Okay, so I know the initial height, 0.70. I know the final compression. Ooh, that has to be changed into meters as well. So don't plug it in as 10 centimeters, it's going to be 0.10 meters. And so now you solve for the unknown. Okay. 1/2, the mass is 2, the initial speed is, 3 squared. The mass again, 2, g is 9.81 on the surface of the Earth. This is 0.7, 1/2 the stiffness, the spring constant, times x final. X final, oh yeah, that was 0.1. And so you solve for k, multiply both sides by 2, right? Multiply the entire left side by 2, and you can cross it out there. And then you divide both sides by 0.1 squared. And what do we get for k? Well, in this problem, k came out quite big. That may not be quite our normal value that we're looking at, but here k is 4,546.8. The units for k are newtons per meter. And that's a really, look at how high k is. That is really stiff, a spring, because of how high the value of k is. So that's how you solve.